The finite square will is made of the potential function v of x equals minus v naught if x is between minus a and positive a, and it's 0 everywhere else if the absolute value of x is greater than a. So if I want to plot this potential, this is our x-axis, this is our potential axis v of x. So this is a, this is minus a. Between a and minus a, our potential function is minus v naught, and less than minus a, our potential function is 0. Greater than a, our potential function is also 0, and here it's v naught. So the Schrödinger equation reads, before we go to the Schrödinger equation, let's notice a few things that we're gonna look at three regions. This is region number 1, this is region number 2, and this is region number 3. Just like the delta function, the finite square will function gives two states, the bound state and the scattering states. So we're gonna look first at the bound states in all of these regions, and then we're gonna look at the scattering states also in all of these regions. So for region number 1, for the bound state, the bound state, that is E, is negative, and it has to be less than minus v naught. So for region number 1, our Schrödinger equation reads minus h bar square divided by 2m, the second derivative of psi with respect to x, equals e times psi. Remember, v of x is equal to 0. So as usual, we're going to find the variable k as the square root of minus 2m times e divided by h bar. Notice that this is the bound state, so e is negative, so this quantity here is real and positive. So the solution for this equation in terms of k, the equation is the second derivative of psi with respect to x equals k square times psi, and the general solution for this, we have psi of x equals a e to the minus kx plus b times e to the kx. And if x approaches minus infinity, because we are looking at the first region, so it can the first term blows up, so we have to force it, we have to cancel it by forcing a to be equal to 0, and the general solution then is psi of x equals b e of kx. Good, so now we're gonna look at the second region where v of x equals minus v naught. This is between minus a and positive a. The Schrödinger equation reads minus h bar squared divided by 2m times the second derivative of psi with respect to x minus v naught times x, times psi, equals e times psi. We're going to define a new variable called L. L is defined as the square root of minus 2m times e plus v naught divided by h bar square h bar. So in terms of L, the Schrödinger equation is the second derivative of psi with respect to x is equal to minus L square times psi, And we also know the solution for this guy. It's psi of x equals c times sine of Lx plus d times cosine of L times x. If you say why I switched to sines and cosines, there's no reason. You can write it in terms of exponential, but you will see this is easier to work with in this case. So this is for x is between minus a and positive a. Okay, so now we can't really set c or d equal to 0 because here x is only between minus a and negative a. So now finally the third region. So this is for x greater than a, and we know for x greater than a the potential function v of x is equal to 0. So the Schrödinger equation reads the same thing, right? So the second derivative of psi with respect to x equals k psi, e psi, right? No, my bad. Equals k squared times psi. So for this solution we have psi of x equals f times e to the minus kx plus g times e to the kx. Again, as x approaches infinity, because we are in the third region, this term blows up, so we have to set g equal to 0, which leaves us with the solution psi of x equals f times e to the minus kx. So now we have all solutions for all three regions. So now we have to put them all together using boundary conditions. It's going to make the problem a lot easier if you notice that the function we're working with is an even function, right? So since it's an even function, we can write the solution for it. Psi of x equals f times e to the minus kx. This is for x greater than a, and here we have d times cosine of Lx. This is for x between 0 and a, and for the rest we have psi of minus x for x less than 0. If you look at the regions where x is less than 0 and take this psi function and put a negative for x, it's going to generate the same solutions. But doing this cuts our problem in half. So we have two boundary conditions. The first one is the psi must be continuous at minus a and positive a. So the first condition is psi and, so this is both 1 and 2, and d psi dx are continuous. At minus a and positive a. So for the continuity for psi of x at x equals 0, so this is x equal a, we have f e to the minus ka equals minus equals d cosine of L times a, right? And for the first derivative, we have minus k, just take one derivative of this, times f times e to the minus k a must equal to minus L times D times sine of L times A. So let's name this equation equation number 1 and this equation number 2. So dividing equation number 1 by equation number 2, we find that, so equation number 1 divided by equation number 2, we get k equals L times tangent of L times A, right? So now for the formula for the allowed energy, since k and L are both functions of E, to solve for E we need to adopt some inner notation. Okay, so here we're gonna create a new notation, so make things a lot easier. Let's create a new variable z to be a times L times A, and we have to create z naught to be equal to A divided by h bar times the square root of 2m times v naught. Alright, so now if we have k square plus L square, this is equal to 2m v naught divided by h bar square. So k and then k times a is equal to the square root of z naught square minus z square. There's a lot of algebra between here, but if you work this out, you will see how this work. Okay, so now our equation goes tangent of z is equal to the square root of z naught divided by z square minus 1. The reason we did this, we need to find these z points. If we find these z points, we find the solution, right? The way we find these z points, we plot each function. We plot the left hand side, and then we also plot the right hand side, and the points where they interact, these are our solutions. So now let's erase this. So now here's our z-axis, is our vertical axis. So the first function, this is looks something like that. This function here is the square root of z naught divided by z square minus 1. And if we plot the tangent, we know the tangent looks like this. So this is tangent of z. So these intersects here, where the two plots interact, are our solutions. Alright, so these are the solutions for the bound state for the wave function psi of x equals to f times e to the minus kx. This is x greater than a, and then we have d cosine of L times x for x between 0 and a, and then we have psi of minus x for x greater than 0, less than 0. So we will normalize these this psi function to find this f and d, but we're gonna do this in a separate video, and the link is at the top right corner here. Alright, so now we're gonna move on to the second scenario where we have the energy is positive, greater than 0. So in this case we have the scattering states, right? So for the scattering states, for region number 1, we have the solution. So for region number 1, the solution is the same, right? We have the same wave function, k squared times x times psi. So now the solution for this one, psi of x equals a e to the I k x plus b times e to the minus I k x. Alright, so this is for x less than minus a. As usual, we have k here is defined as the square root of 2m times e divided by h bar. Alright, so inside the well, where x is between minus a and positive a, we have the solution. So this region number 2, the solution, we have psi of x equals, this is our potential function, v of x equals minus v naught, right? So the solution is c times sine of L times x plus d cosine of L times x. Again, L here is defined as the square root of 2m times e plus v naught divided by h bar. Alright, so now to the right, where x is greater than positive a, so this region number 3, the solution for our wave function, we have psi of x equals f times e to the I k x. Alright, so here a, so if we want to look here, a is the incident wave, right? So this is the incident wave, so going this way. B is the reflected wave, is the reflected amplitude, and F is the transmitted wave. So now F here is the transmitted wave. So we have 4 boundary conditions. The continuity of psi of x at minus a, so this is for the first boundary condition. We have psi of x is continuous at x equals minus a, which follows that a times e to the minus I k a plus b times e to the I k a is equal to minus c times sine of L times a plus d times cosine of L times a, right? And then we also have d psi dx is also continuous at x equal minus a, which gives us I times k times a to the a times e to the minus I k times a minus b times e to the I k a, close brackets, equals to L times c cosine of L times a plus d sine of L times A. Alright, so now we're gonna look at the boundary conditions where when x is equal to positive A. Right? So when x equal positive A, we have the inside the will, we have C times sine of L times A plus D times cosine of L times A. This must be equal to the right side of the will, which is F times e to the I k A. Alright, so now we're gonna look at the derivative, the first derivative, also continuous at positive A, which follows that L times C cosine of L times A is it minus D times sine of L times A equals to I times K times F times e to the I k A. If you wonder why the solution for the, so you know, if you remember, our will is something like that, yeah? So this is x, this is v of x. So this is minus a and this is positive a. Here the solution involves both a times e to the something plus b times e to the something, yeah? Inside the way we have sines and cosines. And here we only have one part of the solution, right? F times e to the something. The reason why we have one part here, only the f, because if you look at the wave's either coming from the left or from the right. So it's the same thing if you look at it either way. So if the wave is coming from here, or if the particle is coming from here, then we must have both A, the instant wave, and B, the reflected wave. We also must have F, which is the transmitted wave. It's nonsense to say F plus G, because what G is G is not going to be there, because there is no reflected wave for the transmitted wave. Same thing follows if the particle is coming from the right, then we would have F and G, F being the transmitted wave, G is being the reflected wave, and then we will have A as the transmitted wave. B, we will set it equal to 0. So that's why we have only this F variable in here. Alright, so now this is the second boundary condition. So now it follows that we have to eliminate. We can't solve all of these, because we have A. How many variables we have? We have A, we have B, we have C, we have D, and we have F. You can count K and L if you want for normalization. So we have 5 variables, 4 equations. We are in a bad situation. So we have to manipulate that, okay? The way we're gonna do it, it's just like in the previous video with the delta function potential. Okay? So now we're gonna eliminate C and D, okay? And we're gonna solve for F and B and F. So let's go ahead and do that. Alright, so B is equal to I times, this is the reflected wave, times sine of 2L times A divided by 2 times K times L times L square minus K square times F. Okay, and then F is equal to e to the minus 2I times K times A times A here divided by cosine of 2 times L times A minus I times K square plus L square divided by 2K L times sine of 2L times A. Obviously, we skipped a lot of algebra in here, but if you go back to the previous video where we did the delta function, you will see what how we follow these steps. Okay, so now the probability for the transmission coefficient T is defined as F squared divided by A squared, right? If we look at the inverse of the transmission coefficient, we will find that T inverse equals to, obviously there's a lot of algebra steps here I'm skipping, but you can do this on your own to practice your algebra skills. V naught squared divided by 4 times E times E plus V naught times sine square of 2A divided by H bar times the square root of 2M times E plus V naught. If we look at the sine term here, this sine term, every time this sine term is 0, we have the transmission coefficient to be equal to 1, right? So this sine is 0 every time this term is equal to n times pi, right? So if we take this term and set it equal to, so we have 2a divided by h bar times the square root of 2m times e plus v naught. This is equal to n pi. So every time this term is equal to n pi, we have the sine to be equal to 0, which means the transmission coefficient equal to 1. So if we solve for e plus v naught, so this is going to be e sub n, because we have these integers n's, plus v naught is equal to n square times pi square times h bar square divided by 2 times m times 2 times a square, which is precisely the allowed energies for the infinite square well. Okay, so now if we want to plot this t, so let's say I'll go ahead and plot it right over here. So this is the energy, this is the transmission coefficient T, and right over here is 1, which means that it's 100% probability that the wave gonna be transmitted. So this plot goes like this. It goes here, touches this, and then comes down, touches again, comes down, touches again, and it oscillates this way. And it touches every time we have this n pi over here. So this is like, you can think of these as the n's. There you have it. It's important to know that in the next videos we're gonna show how we eliminate C and D, okay, and how we solve for the remaining two B's and F's. Because if you remember, we have A and B, we have C and D, then we have F. The next video we're gonna show how we arrived to the transmission coefficient. Basically what the algebra we skipped in this video.